Hello, my name is Erich Walter, and I work at the Naval Information Warfare Center Pacific. I am presenting work we completed recently in collaboration with the Laboratory for Advanced Cybersecurity Research to add deceptive elements to the Microsoft CyberBattleSim open source package. In this talk, I will discuss our reasons behind adding deception to the environment, as well as details about CyberBattleSim and how we changed it to add deceptive elements. I will also describe how we intended our deceptive elements to function, as well as some preliminary results with a sample environment provided as an example in CyberBattleSim. It is typically easier to attack a network than to defend it. But why should attackers expect or encounter the same usability as a valid user? Deceptive elements can impact humans as well as autonomous attackers and help rebalance this asymmetric relationship. Without accurate information about the networks and targets, attackers will take longer to achieve their goals as well as generate more higher confidence alerts for a defender. They may even doubt if they have achieved their own goal, even if they have. In this work, we wanted to investigate the effects of varying the number and placement of two different types of deceptive elements in a network on an attacker whose goal is network ownership. We chose the open-source CyberBattleSim package from Microsoft as it simulates an enterprise network with attackers and defenders. The environment includes a predefined, partially observable network with an attacker foothold. There are typically three types of attacks: local, remote, and connect. The attacker observation space includes attacks available on that node, credentials they have discovered through exploits, as well as the nodes and connections in the network they have observed. Rewards can be customized to the scenario being run. CyberBattleSim also interfaces with OpenAI Gym, facilitating reinforcement learning experiments. We picked the toy capture the flag environment provided in CyberBattleSim that met the criteria for our experiments. We chose this environment for its simplicity and also for the interconnectedness of its nodes. It was not just a linear chain of nodes. It consisted of 10 nodes representing different points in an attack path. From the information contained in the nodes, we inferred the attack path of discovering all of the nodes and used that as a template for our experiments. Originally, there were flags on several nodes that were worth points for the attacker. In this environment, an attacker always controls the client node, or node 0. Each node can contain information about other nodes as well as login credentials to machines. There are three actions for an attacker: local or remote exploits, or command and control exploits. The local and remote exploits can reveal the names and connections of other nodes. The connect and control exploit requires a credential object that matches a username, password, and service of a target node. If matching, this allows the attacker to own the target node and gain access to the information on that node. We used this inferred attack path to design our experiments with a modified version of the capture the flag environment. There were several modifications necessary to change the toy CTF environment to accommodate deceptive elements. We had to define new node and connection types, as well as change reward distributions. We added honeypots and decoys as new nodes, and honey links and honey tokens as new connections. With our goal of network ownership, we gave control of a node 1,000 points and designated owning 6 nodes as winning the game. Repeated actions were penalized 1 point, and the first touch of a deceptive element was set to -100 points, as this would generate a high confidence alert for a defender. Controlling a deceptive node gave no reward. An exploit that worked rewarded 50 points, and one that did not work was worth -1 point. Using credentials on the wrong node or in an improper fashion received a 10-point penalty. Achieving the win condition was rewarded with 5,000 points. The simulation also needed to be altered to allow the accumulation of negative rewards. This slide describes the deceptive elements in more detail. The environment is on the left, and on the right we have cartoons with the inferred attack path through our network and how it has been modified with the addition of deceptive elements. Honeypots are a high-fidelity deceptive node, meaning it looks and acts like a real machine when the attacker interacts with it, but all the exploits yield links and credentials that are invalid. Honey tokens are credentials that look real and may reference real nodes, but generate an alert for the defender when used. Honey links are references to other nodes on the network that don't actually exist. These elements provide high confidence alerts to a defender as well as waste actions and resources of the attacker. For our experiment, we had 3 of these deceptive elements on each honeypot. The other main type of deceptive element we added to the environment was decoys. Decoys cost less for a defender to run in terms of resources. They appear to be real machines and have services running, but they can't be connected to or exploited. There are no actions available on them. They exist to generate an actionable alert for a defender and waste actions and resources of an attacker as they attempt to exploit the decoy. When a deceptive node was added to the network, it is introduced as a clone of an existing node in appearance, but with the appropriate rewards and properties of the deceptive element. This meant for a real node upstream, for example, node 2, from the deceptive element node 3, we also cloned the exploit action that revealed the real node 3 and added an action that revealed the deceptive node 3 in an identical way. The attacker would then be presented with 2 nodes that appear to be the same to choose from for an attack originating from node 2, a real node 3 and a deceptive node 3. While the inferred attack path here is presented as a chain, the attacker can exploit and connect to nodes in different orders and still achieve the 6-node owned win condition. Owning a node is not necessary to progress at some points, and some nodes connect to multiple machines. Due to time constraints, we are showing only the most interesting results for the front-loaded deceptive elements, meaning deceptive elements are added sequentially to the network starting at node 1 until there are a total of 9 on the network. But we also ran backloaded and single deceptive element experiments. CyberBattleSim includes some reinforcement learning agents that can be used within environment and OpenAI Gym to run a simulated attack. All our experiments included no defender, as we were primarily interested in the impact of the deception type and location on the attackers. The 4 attackers we used included tabular Q learning, deep Q learning, a credential exploiting agent, and a random policy agent. The tabular Q learner uses a Q table to look up maximum expected future rewards for actions at each state. This is a good solution for small-sized problems. Deep Q learning uses a neural network for value function approximation, which will be necessary for larger problems and can accommodate a changing network size. The credential lookup agent runs the connect and control exploit on nodes with any credentials most of the time in an attempt to control as many machines as possible. The random policy agent runs a random action at each step of the game. As there were relatively few actions in our game, the random policy agent can perform well. Each attack simulation was run for 5,000 steps and averaged over 250 episodes or games. On the next 4 slides, we will see the same 8 result graphs for the different attackers with deceptive elements in the front-loaded deployment. Front-loaded means the deceptive elements were added sequentially, starting at, but not including the client node, and moving down the inferred attack chain until there is 1 deceptive node for each regular node, or 9 in total. The shaded areas illustrate the standard deviation for each condition. 4 result graphs are shown for each deception type. Decoys in the top red box and honeypots in the bottom green box are averaged over all episodes, win percent, step to win, rewards, and the percent of actions wasted on deception. Here is our summary graphs for the performance of the random policy agent, shown as the red line on the left. The top row shows the results for decoys. We can see the win percent versus number of decoys graph on the left shows the addition of decoys impacted the win percent, reducing it from 80 to 40% up to 6 decoys, before flattening out after 6. This may be due to the win condition being set at 6 nodes. The next graph, showing the mean number of steps to a win condition, increases 500 steps up to 6 decoys, then levels off at 3,000. The next graph in the top row shows the mean rewards as a function of steps in the game. No decoys gave the highest reward, and 9 decoys had reduced this mean from about 7,000 to 2,000 points. 1 and 2 decoys had reduced this mean by about 2,000 points. We also examined the wasted actions as a function of the number of decoys. We can see that the percent of wasted actions increased about 2% per decoy until about 6 decoys, again, the win condition. The random policy agent performed surprisingly well and similarly to the deep Q learner, most likely due to the small nature of the action and state space. The credential lookup agent, shown as the green curves on the left, won 0 times in all the trials, so the first 2 graphs for honeypots and decoys don't show too much. When we look at the rewards graphs for decoys, we can see that the credential lookup function can get stuck in a negative reward loop with some decoy locations and makes no further progress. About 1/3 of the attacker's actions are wasted with decoy connection attempts. The rewards graph for honeypots follows a trend of more and more honeypots yielding fewer and fewer rewards for the attacker. The honeypots are targeted for connections at a lower wasted action percent than the decoys due to the presence of the honey tokens. The attacker also used honey tokens to try and connect to real machines for more wasted actions, which we unfortunately did not count in this test. The tabular Q learner, the orange curves, performed the best on the attackers tested in all of the metrics. It had the highest win percentage for decoys and honeypots, and took the fewest steps to get there with the most rewards. The addition of decoys did reduce the win percentage moderately, but it did not increase the mean steps to win after 3 decoys. The mean reward decreased a few hundred points for the addition of 1 decoy, but a few thousand points for the addition of 1 honeypot, and brought the rewards below 0 after 6 honeypots. No attacker won after 6 honeypots were added to the network. The percent wasted actions leveled off after 5 decoys, but kept increasing with each additional honeypot. This again may be due to the attacker winning in the case of the decoys. The deep Q learner, the blue curves on the left, most closely resembles the random policy agent, performing similarly across all the graphs. There was a slight difference in wasted actions for the honeypots, indicating a preference for remote connections over local connections. With some tuning of hyperparameters and a different feature selection, we expect this performance can improve. To summarize, tabular Q learning performed the best in all of the tests we ran with decoys and honeypots. The random choice agent performed fairly well due to the small number of valid actions in each state. Honeypots were more effective than decoys at delaying attacker victory across all attackers. The high-fidelity nature of honeypots comes at an increased cost in configuration and maintenance to defenders compared to decoys, which is not yet modeled in this work. Future work, including this cost for a resource-constrained defender, is likely to show that decoys are a better choice in many cases. The location of the deceptive elements matters a great deal to the attacker, and both honeypots and decoys were able to generate actionable alerts early in the attack chain. We successfully added some deceptive elements and experimented with them in CyberBattleSim. The way the deceptive elements affected attacker performance aligned with our intuition. We also observed that honeypots were more effective than decoys due to their higher fidelity, and that the number and location of these deceptive elements affected the attacker's behavior. This provided a sanity check that deception, which is often excluded from cyber simulators, can easily be modeled and is unlikely to impact the generalizability of the learned results. For future work, we would like to add other attacker goals, as well as reinforcement learning-based defenders with control over the deceptive elements. We would also like to inform the models and the rewards with insights from real-world attack behavior gathered from human subject experiments. Here are some references to cyber defense-related work with cyber deception. Thank you for listening.